All right, so we've got problem 5. We have air entering the compressor of a cold air standard Brayton cycle. Tells us K is equal to 1.5 or 1.4. So that is another way of telling us that the specific heats are going to be assumed to be constant. So yeah, I've got that right over here. Cold air standard, K is equal to 1.4. And then you can also look in your in table, let's see, go. You could look in table A20, and you can see that at K equal to 1.4, you've got a corresponding CP value of 1.005 kilojoules per kilogram K. All right. And then we've got a couple of other things. So the air enters the regenerator at 290 Kelvin. Um, sorry, it enters. Oh, I'm sorry. Enters the compressor at 290 and 100 kilopascals. The pressure ratio is 8. The temperature of the air entering the turbine, and I guess that's one thing that is not on there, so we should put that on there. Temperature of the air coming in at T4 is 1370 Kelvin. That's not on our table or on our diagram there. And then we're given an isentropic efficiency of the compressor and the turbine. They're each 90%, and then the regenerator effectiveness is 90%, and that should have been I guess on the figure it says 0.7, but really let's change that to 0.9. So 90%, 0.9. Let me kind of make that a little bit more clear. So 0.9. We're supposed to find the thermal efficiency of the cycle, and it looks like we also want to find the back work ratio, although it wasn't in the certainly wasn't in the problems or in the problem statement. So I don't know. We can get an equation for it if we want to. I guess that would be a good idea. So all right. So the first thing that I'm going to do is I'm going to apply my first law and get my equations for the work ins and the work outs and all that stuff. Now, one thing that you'll notice is that this is not a closed loop because remember, the gas turbine engine, it's not a closed loop. But what we do is we imagine that exhaust process is really replaced. I kind of draw it through there. Um, it's really replaced with an imaginary heat exchanger. So we're modeling the exhaust process as a constant pressure heat rejection process. So I'm going to write this not as Q dot, but I'll write it as Q out because I don't think I actually have enough information to find a Q dot. I don't actually know a mass flow rate, so I'll write this as Q out. And then while I'm at it, I'm going to go ahead and draw my Q in because I do have a Q in as well right here. Here's my Q in. So this is where we're modeling that combustion process. Okay, so and I guess I will also maybe put my Q or my work ins and my work outs. So from 1 to 2, that's an ideally isentropic compression process. Compression is a work input. So that's a lowercase w, and then I'll put a little lowercase w in right here. Um, Now, if you're wondering what about the regenerator, because I know, I do know that there is going to be heat that's going between that top little squiggly and the bottom squiggly, but I don't count him as a Q in or a Q out when I talk about the cycle as a whole because he's not leaving the cycle. I'm just moving heat around within the cycle. So it doesn't count as a Q in or a Q out when you're calculating things like thermal efficiency. All right. And let me do something really quick. I think this a little bit. There we go. A little bit more centered there. All right. So first things first, let's get our equation for thermal efficiency. So I can do this two ways. I can write this as work net out over Qn, which is any work in minus any work out. So, and I have one of each, right? I have a workout between 4 and 5. I have a work in between 1 and 2. And then my Qn occurs between 3 and 4. So this is a good time to go ahead and maybe apply my first law. So first law, I'm just going to write it up here just so I have it. So dE dt equals Q dot in minus Q dot out minus W dot out minus W dot in. And then all of this plus the sum of a whole bunch of stuff coming in. M dot times H plus kinetic energy plus potential energy. I know I'm going to ignore those, but might as well just put them there now, just so I know that they were once there. So enthalpy plus kinetic energy plus potential energy. All right. Now, one thing that I absolutely can do is I can go ahead and say, well, it's steady state, right? I said that up here, it's steady state. And I also am ignoring the changes in kinetic and potential energy. So I'm going to go ahead and cross those guys out. And now I'm going to take this information and I'm going to, let's just work around the cycle. So I'll put like a little thing where. So let's start with the work in. And really this is going to be W dot in. This is going to be, so it's the sum of the M dot H's. If I apply my first law, right, it's going to be the sum of the M dot H's going out minus the sum of the M dot H's going in. So out minus in. And so this same mass flow rate going in and out. And I know that because I could do a mass balance, right? Apply my conservation of mass and prove to myself that that mass flow rate, because it's steady state, because it's one inlet, one outlet, that mass flow rate is the same. So this becomes M dot times H2 minus H1, or M dot times CP times T2 minus T1. This is just M dot times that little work in. All right. And I could work my way around the cycle, right? So the next heat or work input that I come to, or output that I come to, is between 3 and 4. So this is where I'm modeling my combustion process. So this is going to be, and it's the sum, if I apply my first law, cancel all this stuff out, it's going to be all the stuff going out minus all of the stuff going in. Okay. And I could go through the same kind of thing, same little song and dance. It's a delta H, which I can, because it's an ideal gas with constant specific heats, I can say that this is M dot times CP times T4 minus T3. And this is just another way of writing M dot times little q n. All right, keep on going around. Same thing with my W dot out. This time when I apply my first law, it's going to be the stuff going out. Once I cross out this, once I cross out this guy, this guy, this guy, it's going to be the sum of the things going in minus the sum of the things going out. And so it's going to boil down to M dot times CP times T4 minus T5, or M dot times little w out. And then finally, I have my Q dot out. So this is going to be M dot, and it's going to be, if I apply my first law, lots of stuff going away, it's going to be the sum of the things going out minus the sum of the, let's see, it's Q dot out. It's going to be the sum of the stuff going in minus the sum of the stuff going out. So this is going to be M dot CP times what's going in is it going to be at 6. What's going out is going to be at 1. All right. So it's going to be T6 minus T1. And again, that sort of mental exercise about which temperature is going to be higher works here too, right? I know all of these are going to be delta H's. They're all going to boil down to CP delta T when I apply that constant specific heats assumption, that cold air standard assumption. And so it's just a matter of which temperature is the highest. Well, the temperature T6, for example, T6 is bigger because your temperature is going to be higher before you reject the heat than after. And then this just becomes M dot times little q out. So now it's really easy for me to go back up to that thermal efficiency equation. And I have, so little w out, that's going to be that line right there. So it is going to be, I've got CP times T4 minus T5 minus the little work in right there. So CP times T2 minus T1. So T2 minus T1. And then this guy down here, Qn, is just going to be CP times T4 minus T3. And of course your CPs, yes, they're going to, they're going to cancel out, sure. But there you go. You can also put this in terms of 1 minus Q out over Q in. Right? That would be fine too. So this would be 1 minus, and the CPs are going to cancel out. So on the top, you're going to have a CP times your T6 minus T1 over CP times T4 minus T3. And of course, again, your CPs are going to cancel out. So it doesn't matter that I didn't write them. They just go away, right? So either way that you decide to calculate it, whether you decide to use this equation or you decide to use this, this equation right here, it should not matter. You should get the exact same thing. So I have my governing equation. I'll put a little, I'll get some answer right here. I'll put a happy little bubble to designate where that's going to go. My back work ratio is the work of the compressor over the work of the turbine. Well, work of the compressor is the work input. Work of the turbine is my work output. Oh, and I realize somebody is like screaming at me because I just realized this up here. This is not a work. That's not a work in. That's a work out. So hopefully you read my mind about what it should be, but yeah, if you didn't, that's what it is. So the workout. Okay. So now that back work ratio just becomes, all right, so I've got my work input, this guy right here, over my work output, which is this guy right here. And of course, the CPs are going to go away. And that, by the way, that I should be crossing this and this because I'm putting it in terms of little w, not w dot, but there we go. So work of the compressor. So this is going to end up being T2 minus T1 over T4 minus T5. And I don't know what that is, but I'll put a happy little bubble there. This would be, because there are no unit conversions that are necessary here, this would be enough to get you the full points for, what is the thermal efficiency? Well, you've given me the governing equation in terms of temperature. You've given me the backwork ratio in terms of temperature. This would be enough for full points for that. You just need to figure out those unknown temperatures. So let's go look. So let's see. So I know T1. I need T2. So I'm looking right there. All right. Well, I have an isentropic efficiency that's given to me. So I know that I'm going to have to figure out not only a T2, but I need a T2S. I need a T2S first, then I'm going to use my isentropic efficiency to get the T2. So let's do that. So I will write, I'm going to write it, I'll write it like in a purple here. All right, so state 1, and really the only thing I just need the temperature, and I already know the temperature, T1, 290. Okay. And then the next thing that I need state 2. So I am going to put a little spot for 2s, and then I'll get 2, because state 2 is going to be used state 2 is going to be calculated using the isentropic efficiency for my compressor. So it's the ratio of the two works. Ideally, we don't have to put a lot of work into it. That would be the smaller number. So that's going to be on top. It's a delta H or a CP delta T. I've already calculated what that would be, right? So this is going to be, yes, the CP goes away, and I wish now that can I change this? Yeah, perfect. Okay. All right. So this is going to be a CP delta T CP T2S. Oh, one at blue, one at black. T2S minus T1 over, and now I have a CP T2 minus T1. So once I get that T2S, I'll be primed to get T2. So when I plug things into my equation sheet, my governing equation, that's what I'm going to be using. Okay, so now I need to figure out state 2s. Then for that, I'm going to use an isentropic relationship. And I can use the one for constant specific heats. So it's going to be T2s over T1, which is equal to P2 over P1 to the K minus 1 over K. And I know P2 over P1, it's 8. They gave us that. They gave us the pressure ratio. So I'm all good there. I just need to plug in some numbers. So my T2S ends up being 525.32, which means that the T2 has got to be 551.5. So 551.5 Kelvin. All right, perfect. So state 3. All right, well, let's go see what we have. What's going on with state 3. So state 3 is up here right after we have gone through that regenerator. And it's not an isentropic process. I don't really, I don't have like a cue given to me from that top little squiggly from 5 to 6. The only thing that might help me is maybe the definition for that regenerator. So let's use that. So I know that my regenerator, I'm definitely going to have to add another piece of paper here, I think. Definitely. Not that one. That one. Okay. All right. So my regenerator, I know this guy. In fact, I think I'm going to erase this, clean that up a little bit, just a tiny bit. Yes, I know it's going to be that one will be 0.9. And I know that this is Q regen over Q regen max. Okay. I'm going to go ahead and skip to the chase about the Q regen. It's going to be a delta H, right? Draw my control volume around that bottom squiggly. It's going to be a delta H, H3 minus H2, or in terms of CP delta T, CP times T3. T3 minus T2. And then my Q regen max would be if by the time your working fluid flowed from state 2 to state 3, it had heated all the way up to the same temperature as T5. So CP times T5 minus T2. And so that's the equation that I'm going to use there. Let's go back here. I'll put my governing equation here to find state 3. So I know that my regenerator effectiveness is 0.9, and I just figured out that it's CP times T3 minus T2 over CP times T5 minus T2. Obviously, those CPs are going to cancel out, and I should get that my T3 is equal to, it'll be T2 plus that regenerator effectiveness times T5 minus T2. And no, I don't know yet what T5 is, but that's okay. I'm just going to keep on working my way through the cycle, and hopefully I will come across what T5 is. So, all right, so now we got state 4, and state 4 is actually given to me, believe it or not. That was given to me, was written on your diagram, but it was given to you right before it goes into the turbine. E4 1370. All right, so now we got state 5. Perfect. Now, if you'll notice, between 4 and 5, we've got expansion through the turbine. Ideally, that would be an isentropic expansion, but you'll notice that we have an isentropic efficiency associated with that turbine. So we need to calculate T5S, and then we need to calculate T5. So let's do that. All right. So I need 5S and I need 5. Okay, because state 5 is going to be found using the equation for my isentropic efficiency. So isentropic efficiency for my turbine, it's the ratio of the two works. Ideally, isentropically, you get a lot of work out of it. That would be the bigger number on the bottom. But in reality, because of irreversibilities, you're going to get less. So this becomes, and we already calculated that work output right up here, right? So let's go ahead. And so this is between 4 and 5. So I got a CP times T4 minus T5. Oops. Over CP. CP times T4 minus T5S. And of course, that means that we have to figure out what T5S is. Let me pause this just for a second. Okay, I think I fixed it. I had a little button that kept on selecting the wrong thing, and it was annoying to me. I didn't want to have the whole lecture like that. All right, so should be able to get T5 from this once I get T5S, and T5S is just going to be another isentropic relationship. So T5S over T4 is equal to P2, I'm sorry, not P2, P5 over P4 to the K minus 1 over K. Let's see if I know P5 and P4, or if I know the ratio between those guys. Let's go up here. All right. So remember, one thing that we're assuming is that You know, this is an ideal cycle except for those isentropic efficiencies. So no heat transfer where I don't want it to happen, and also no pressure drops. So I went ahead and actually wrote it over here. So if I walk through P2, P3, P4, those are all the same. There's no pressure drop across those heat exchangers. And then again, P5, P6, no pressure drop across that little top squiggly in the heat exchanger, and no pressure drop across the imaginary heat exchanger that I've drawn there to model the exhaust process. So, since I'm trying to find P5 over P4, well, P5 over P4, this is going to be the same as P1 over P2, which is just 1 over 8. So let's go back to our equation, 1 over 8. So this is going to be 1 over 8 to the k minus 1 over k. And so I've got a T5S. Let's see what he is. T5S ends up being 756.3. And then my T5 ends up being 817.7 Kelvin. And I'm going to highlight that guy because I'm going to plug him into my governing equation. And now I'm also ready to figure out what T3 is. Because now I have this guy, I have T2, I have epsilon, I've got the regenerator effectiveness. It's just plug and chug. And so I get a T3 of 737.8 Kelvin. Perfect. Now, I kind of don't need T6 because, you know, I could just, when I'm calculating, yeah, I don't need it for the backwork ratio, right? I don't need it for this guy. But and then if I look at my thermal efficiency equation, if I use this equation, I don't really need it, but I think I'm going to calculate it anyway because you may be asked on a test to just calculate all the unknown temperatures anyway. So let's go ahead and think about how we would do that. I really have two options for expressing that regenerator effectiveness. So let's actually want to erase that, and that. Okay. So if I drew my control volume around this little guy, so this is 5 and this is 6, that Q regen leaving that little control volume would be T5 minus T6. Oops, I think I need that a little bit smaller. So T5 minus T6. Or, or not or, but when I'm calculating the maximum amount of heat that could be transferred out of that little control volume, it would be if by the time that working fluid had flowed from state 5 to state 6, it had cooled all the way down to the lowest possible temperature it could be at, and that would be the incoming temperature at T2. So on the bottom, it would be T5 minus T2. Okay, so 5 minus 6, 5 minus 2 on the bottom. Okay, so let's do that. And let's also make this a little bit bigger. So state 6, we really got two options here. I'm using the regenerator effectiveness as one of them. So on the top, it was T5 minus T6. On the bottom, CP, T5 minus T2, right? And so you can get a T6 that way. That's option one. And when I do this, I do get 631.3 Kelvin. Now there is another way if you prefer to think of it like this. So I'm going to redraw my regenerator down here. Okay. All right. So this is 2, this is 3, this was 5, this is 6. I could choose to draw my control volume around this whole thing. Okay. If I do that and I apply my first law to this entire thing, yes, I have heat transfer going on within the confines of this thing, but I do not have any Q crossing that red dotted line. So if I apply my first law, dE dt equals Q dot minus W dot, or Q, I'm sorry, equals Q dot M minus Q dot out minus W dot out minus W dot in, that whole thing, you're not going to have, if it's steady state, changes in kinetic and potential energy. Where is it? Yeah. Here's my first law up here. Okay. I'm going to cross these out though again. If I apply my first law, steady state, no changes in kinetic and potential energy, and no Q dot or W dot, the only things that I have left are the sum of the M dot H's coming in and out. So let's go look at that. So first law gives me that the sum of the M dot H's coming in equals the sum of the M dot H's going out. So I have M dot H2 plus M dot H5 equals M dot H3 plus M dot H6. And I could put those in terms of, I could get it in terms of deltas or whatever, but what I'm going to end up getting, I'll have the M dot is just going to go away. I mean, I guess that's pretty obvious, right? There's one in all of these. I could get things in terms of delta H's. So this would be CP H2 minus H3 becomes T2, CP T2 minus T3. H6 minus H5 becomes CP times T6 minus T5. And so you can solve for T6 that way, and you should get the same thing, 631.3 Kelvin, right? So however makes sense to you is fine. So once we've done that, plug this guy, plug all those temperatures into my thermal efficiency equation. Let's see what I end up getting. I've got 46%. I actually do not have a number for the backwork ratio here, but it really is. It's just plug and chug. So yeah, just plug and chug. All right, so if you want to take a screenshot, screenshot 1, screenshot 2. All right, we'll do the next problem. All right, so on to the next problem. This is a problem, the next problem uses reheating, or talks about uses reheating and intercooling. So this is another means of increasing the thermal efficiency of your gas turbine engine. So if you have not watched the video for reheating and intercooling, please just stop this video right now, go watch the video, and then come back to this point. But what it is it is a way to increase that thermal efficiency by increasing the work net output. The work output is going to be increased by reheating. So what they do is they divide up those turbines. They divide up the expansion within the turbine into not one stage of expansion, but 2 stages of expansion. So you'll see 2 turbines, a high pressure and a low pressure turbine, and you'll see a heat exchanger in between. And this is your reheat combustor, which we're just, like I said, we're modeling it with a heat exchanger. And then we can also try to decrease the work input to increase that thermal efficiency. And we just kind of do the opposite thing with the compression. We divide it up into 2 compression processes instead of one single compression process. So instead of using one stage to achieve a pressure increase from this pressure to this pressure, we divide it up right, two compression processes, and in between those compressors, we add in a intercooler, just a heat exchanger. You're just removing heat from the system. You're keeping it cool. So, yeah, the way, well, let's work through a problem and then we'll talk about how I kind of remember things. All right, so this right here is a cold air standard Brayton cycle that gives us K is equal to 1.4. If we don't remember what CP value that it corresponds to, you can look in table A20 to see that it corresponds to a value of 1.005 kilojoules per kilogram K. But anyway, regardless, we have an ideal cold air standard Brayton cycle with reheat, and the reheat is occurring right here. So essentially, the way to remember, is it a Q in or a Q out? I think of it, I'm fighting against what's happening. So with the turbine, as you expand between 5 and 6, the pressure's going down and the temperature's going down. But, oh, I want to fight against that. I'm going to keep it up. I'm going to add a Q in. Okay, so that's my reheat stage. And then my intercooling stage is right here. So I'm fighting against what's happening. Pressure goes up from 1 to 2 in that compressor. Pressure goes up, temperature goes up, but I'm going to cool things back down. I'm fighting against it. There's my Q out. 4 to 5, this is just the main combustion process, which I am modeling as a simple heat addition process. Okay. All right. So I think I can see I've got some numberings wrong, but let's get to it in a second. So we have air passes into the first compressor at 300 Kelvin, and the pressure across that first compressor is 3. And then it's cooled and it enters the second compressor at 300 Kelvin. Pressure ratio across the second compressor is 3 as well. Once that air exits the second compressor, it undergoes a combustion process from 4 to 5 and enters the first turbine at 1200 Kelvin. So I can see already that I've got like a little bit of a typo there, because that should not be T1. This guy should really be T5. And I believe this one is going to be T7, but we'll verify in just a second. All right, so once that air enters the second compressor, it undergoes the combustion process, enters the first turbine at 1200 Kelvin, expanding to a pressure that is 1/3 that of the inlet pressure. The air then enters a reheat combustor, so that's from 6 to 7, and enters the second turbine at 1200 Kelvin, that's T7, expanding to a pressure that is 1/3 that of the inlet pressure. And then they do give us some isentropic efficiencies, but they're 100%, so that's super convenient for us. So we'll talk about that in just a second. We want to find the backwork ratio and the thermal efficiency. So there you go. I went ahead and I wrote my Q ins and my Q outs, but I might as well go ahead and write, where my work in and my work out is. So this guy is a work in. This guy is a work in. This guy is a workout. This guy is a workout. And the governing equation to figure out the Q ins and the Q outs, so the work ins and the workouts, is just applying that first law, right? So your dE dt equals Q dot in minus Q dot out, that equation right there. So you'll get things in terms of delta H, which, because we're making that assumption, cold air standard assumptions, I'm going to put that delta H in terms of CP delta T. This becomes CP. This one's between 1 and 2. It'll be T2 minus T1. Again, apply your first law and derive it, or it's going to be in terms of delta H's, which of those T's is bigger. Or I'm sorry, you'll know it's in terms of delta H's, which you can approximate as CP delta T's, and you know which one of those CP's or which one of those temperatures is bigger. All right, this one is between 3 and 4. This becomes CP times T4 minus T3. Let's do the Q out. This is between 2 and 3. Well, the temperature is going to go down. So T2 is the bigger one. T2 minus T3. I've got a QN up at the top. Which one's going to be bigger is going to be the temperature at the end of that heat addition process. T5 minus not T5 minus T4. T5 minus, not T5 minus T5, but T5 minus T4. Then I got another QN, got another one down here. This becomes CP times T7 minus T6. Perfect. Got a couple of workouts between 5 and 6. Well, the temperature T5 is going to be bigger, right? Pressure's going down, so is that temperature. This guy is going to be CP times T7 minus T8. There we go. And we've got one more heat exchanger that I kind of forgot about until now, but this is where we're modeling our exhaust process. This is another Q out. All right, so it's between 8 and 1. T8 is the bigger one, so T8 minus T1. All right, so boy, I've actually done a lot of work here. So I should be able to very quickly get a governing equation in terms of CP delta T's for my thermal efficiency and my back work ratio. My thermal efficiency, I have a choice to either put it in terms of work net out over QN, and I would encourage you calculate it like that. Make sure that you get the same value. So it would be this guy plus this guy minus this guy minus that guy over QN, all the QN. Or you put it in terms of 1 minus Q out over QN. And when we write QN and Q out, we're talking about all the QN, all the Q out for the cycle. So, all right, so the Q out, I got two of those terms. I got a CP, I got this one, CP T2 minus T3, and then I've got another one, CP T8 minus T1. Perfect. And then I've got my QN, which is this guy and this guy. So I got the primary combustion process, CP minus T4 plus CP times T7 minus T6. Perfect. And of course, that CP is going to go away. Those are going to get divided out. And I'm going to get a final answer here. All right. And then my back work ratio. Work of the compressor, and it's both compressors, right? I got two of them over the work of the turbine or turbines. I'm not going to put like S because that might make me think isentropic, and I don't want to think of that. So, all right, well, there's no good way around this. So I've got on the top work of the compressors. So I've got CP times T2 minus T1 plus this one, T4 minus T3. Okay. And then on the bottom, I've got the work of the turbine. So this and this. So I have CP times T5 minus T6 plus T7 minus T8. Perfect. And of course, the CPs are going to cancel out, and I should be left with some number here. All right. So now I got to figure out my temperatures. Easy peasy. And I know half of them. I know 1, 3, 5, 7. Just need the other things, right? So I will go ahead and I'll write, I like writing state 1. Here's state 1. State 1, T1, 300 Kelvin. State 2. All right. Now, lucky enough for us, 2 and 2s are exactly the same, state 2 and state 2s, because my isentropic efficiency is 100%. How do I know that? Because they told me. The isentropic efficiency of the compressor and the turbine, both of them, is 100%. So I don't need to worry about using an isentropic efficiency equation. When I calculate T2 with that isentropic efficiency equation, that is T2. P2 over P1 to the K minus 1 over K. I know P2 over P1, it's 3. I know T1, and so it's just a matter of solving for T2. So I end up getting 410.625 Kelvin. And I think I'd like to highlight the temperatures that I'm going to plug in. I guess it's really no no shock as to what I'm going to be using here. But all right, now I got state 3. That's given to me. T3 is the same as T1. And now I've got state 4. So T4, I'm going to use, and that second turbine there, this, or the second compressor there, it's also operates isentropically. So, you know, I can make a note that T4 and T4S are exactly the same, right? So when I apply my isentropic relationship, yes, that's T4S, but it is T4 because my isentropic efficiency is 100%. And then I am also given the pressure ratio across that second compressor. It's also 3. So, well, if you look at those numbers that we're plugging in, it ends up being, of course, the same as T2. So here we go. Same inlet conditions, same operating conditions. So no big shock there. And then I've got state 5, which I know. I think that's given to me. Yes. Yes, it's given to me. T5 ends up being 1200. State 6. So state 6 is after that first expansion process in the turbine. And again, they told us that those turbines operate isentropically. So when I apply my isentropic relationship and I solve for T6S, that is T6. So there we go. So T6 over T5 equals, P6 over P5 to the K minus 1 over K. So I end up getting a T6 value of 876.72. Perfect. All right. I'll highlight that guy. State 7 is given to us because T7 and T5 are the same. And amazingly enough, it is the exact same. So state 8 is coming out of that second turbine, which operates isentropically. It's the same operating conditions, the same inlet conditions as that first turbine. So I should not be surprised to see, shouldn't be surprised to see that my T8 ends up being the same as my T6. There we go. So easy peasy. So when I plug things in, I'm going to get a back work ratio of 34.2%. And then I've got my thermal efficiency 38.2%. So if you would like to take a screenshot, I guess, I'll put that right there. And we will go on to the next problem. All right, so problem 7, we have air enters the compressor of a regenerative cold air standard Brayton cycle. So enters state 1 at with a volumetric flow rate of 60 meters cubed per second, pressure of 0.8 bar, temperature of 280 Kelvin. The compressor pressure ratio is 20. The maximum temperature, my maximum cycle temperature is 2100 Kelvin. And so it doesn't say point blank that this is at state 4. But we can reason out why it's the highest temperature, right? So 1 to 2, pressure goes up, temperature goes up. 2 to 3, it's going to go up a little bit more because we've harnessed some of that waste energy through regeneration. But then 3 to 4, that's the primary combustion process. And so T4 is going to be way up there. And then we're going to cool down as we expand from 4 to 5, 5 to 6. is where some of that waste heat is leaving the air, right, between 5 and 6, and going down to between 3 and 2. And then, of course, between 6 and 1, what's going on there over there? Well, it's not shown, but that's okay. It doesn't matter. That's our exhaust process, and we know that we are going to model that. It's just a simple heat rejection process. Sometimes, in your textbook, they usually don't write this, and it would just be kind of up to us to know that, okay, well, that's the exhaust, and we're going to model that as an exhaust process. So I'm going to put a little, here's my Q dot out. And then while I'm at it, let's go ahead and here's my W dot in. Here's my W dot out. I do have a Q dot in for that primary combustion process. All right, so let's continue reading through the problem statement. So got the compressor ratio is 20, maximum cycle temperature is 2100. For the compressor, the isentropic efficiency is 92%, and for the turbine, the isentropic efficiency is 95%. The regenerator effectiveness is 85%. We want to find the net power developed in megawatts. So that's a W dot term. We want to find the thermal efficiency, and then we want to find the rate of heat addition in that combustor. So that's that Q dot in. You will also notice that I went ahead and wrote the first law up at the top just so we have it. All of these problems, just like the ones that we did before, we are assuming steady state. So dE dt goes away, and changes in kinetic and changes in potential energy are negligible. All right. So before we go further, I think I'd like to at least get some governing equations for our Q dot in, Q dot out, W dot in, W dot out, just so we have them. So let's start with our W dot in, since that's between 1 and 2, and just kind of work our way through the cycle like that. So we have W dot in. If I apply my first law up here, everything but the W dot in is going to cancel out, and I'll see that this is going to be, it's going to be the stuff going out minus the stuff going in, and this is going to be m dot delta H, right, between 1 and 2, right, H2 minus H1, but I could put this in terms of Cp delta T. Now I've got my Q dot in. Let's do him next. So if I apply my first law, I'm going to see that it's going to be, all right, so this is going to be the sum of the m dot H's going out minus the sum of the m dot H's going in. Perfect. So it's going to be a delta H between 3 and 4, H4 minus H3, or m dot times T4 minus T3. And now we're at our W, let's make that our W dot out be a little bit smaller. So this is going to be the m dot H. This one, when I apply my first law, it's going to be the stuff going in minus out. So in minus out. All right. This ends up being m dot Cp times T4 minus T5. And then work my way around between 6 and 1. That's where I am modeling our exhaust process, and that's my Q dot out. It's going to be stuff going in minus stuff going out. Again, that little mental exercise about which temperature is the higher one still applies, and you'll get m dot Cp times T6 times T1. So you can see the, I'm going to put an m dot on all of these. Don't worry, I'm going to write something else. This is little work in, this is little q in, this is little work out, This is little Q out. All right. First thing I'm supposed to do is I'm supposed to get W dot net out. So let's go ahead and start getting our equation for that. We've done all the hard work, really. So yeah. So my W dot, I'll say this is a W dot net out. It is any of the W dot out minus any of the W dot in. So I have M dot times, actually there's going to be a CP on the outside of all of this. So it's going to be the stuff going out, T4 minus T5, minus the stuff going in, T2 minus T1. All right, so clearly I'm going to need to find those guys, to find those temperatures. However, I can go ahead and at least get that M dot, because he's going to be function of my volumetric flow rate over here. So if you look on your equation sheet, you have an equation for volumetric flow rate, and this guy is going to be V dot over the specific volume, and this is all evaluated at 1, which would give you the mass flow rate at 1, but M dot 1 is the same as M dot 2, as M dot 3, as M dot 4, and 5, 6, so it doesn't really matter. All right, so I got the same thing. I'm going to rewrite it one more time, because now I can get this specific volume. So that specific volume, well, remember, you have an ideal gas. So that specific volume you can write as R T1 over P1. So we'll plug those things in shortly. One thing that I don't actually have given to me is what is that specific gas constant. Remember, specific gas constant, it is related to your universal gas constant and your molar mass. So if you look on your conversion factor sheet, there are 3 values for that R bar given to you. And the first one is 8.314 kilojoules per kilogram K, or not kilogram K, but kilomole K. And then this guy, your molar mass, you can find in table A1. For air, it is 28.97 kilograms per kilomole. So you end up getting a specific gas constant, 0.287 kilojoules per kilogram K. Right, your universal gas constant is a per kilomole property, or parameter quantity. Your specific gas constant is on a per mass basis, so kilojoules per kilogram K. All right, so I think we've almost got things. In fact, I might want to, let me go ahead and, this guy is 60 meters cubed per second. I'm going to bring the pressure up to the top because it's the denominator of the denominator. So he's going to come up here in the numerator. So my pressure, it's given to me in bar, but if you put it in kilopascals, your units are going to work out. I'll leave it to you to make sure that you agree with that. But 0.8 bar is 80 kilopascals. And then your specific gas constant, 0.287 kilojoules per kilogram K. And then your temperature at state 1, 280 Kelvin. So you can reason out why the units are going to work out the way they are. Kilopascal is a kilonewton per meter squared, and a kilojoule is a kilonewton meter. Okay, oops. And then, yeah, so that's this guy. And then you've got your CP, so 1.005 kilojoules per kilogram K. And I know I haven't found those temperatures yet, so I'll just put them here, T4 minus T5 minus T2. I'm going to distribute that negative K. So you can see that when things, when everything kind of distributes like the units and stuff, let's look and make sure. So I have kilonewtons, kilonewtons, kilopascals, kilopascals. Kelvin will cancel out with these guys over here. Kilojoules, kilojoules. Actually, wait a minute. I think I went, perfect. I was afraid for a second. Kilogram, kilogram, Kelvin, Kelvin, meter squared. Yeah, those meters will cancel out. I should be left with kilojoules per second. Is that what I think I have? Is that what I'm supposed to find? Yeah. So we should get something in kilojoules per second, and I'm supposed to find it in megawatts. So I know a kilowatt is a kilojoule per second, and I know a megawatt is 1,000 kilowatts. And so that should get me my final answer here once I figure out what all those temperatures are. Perfect. Something megawatts. Perfect. All right. Next thing I'm supposed to find, I'm supposed to find the thermal efficiency. Let's go ahead and get that. You could put it in terms of work net out over Qn, or you can put it in terms of 1 minus Q out over Qn. It doesn't really matter. Um, just, and again, it's probably a good idea. Calculate it both ways, see if you get the same thing. So I'm going to put it in terms of 1 minus Q out over Qn, but again, it doesn't really matter, whatever you want to do. All right, so I've got my equations for Q out and Qm. Q out is Cp times T6 minus T1. Qn is Cp times T4 minus T3. All right, so I should get a value for that, and that's just plug and chug, and the CPs are going to cancel out. And then the very last thing I'm supposed to get is the Q dot N, so the rate. Q dot N, the rate of heat transfer. So I probably do need to get this guy right here. I'm going to actually highlight him. That whole quantity, remember, that is my mass flow rate. I think I will go ahead and maybe I should get an answer for him. Get a value for that guy if I have it. If I don't, then I'll calculate it right now. Okay, and I got it. So I have got a value of 59.73. And this is going to be in kilograms per second. So this Q dot N is it's just going to be between 3 and 4. I've already got an equation for this. So this ends up being Cp times T4 minus T3. Perfect. So I should get something, when I calculate it, it's really going to be in terms of kilowatts unless I put it in megawatts. I don't know if I was supposed to find that. It doesn't really matter. I'll calculate. It didn't tell me what units it wanted it in, so whatever is most convenient to you. All right, so now I need to work my way around and get all the states. So let's do that. All right, so hopefully you have the picture in front of you because it will be a little bit difficult to have all the have the picture in the screen. The T1 is given to us. T1, 280 Kelvin, check. Then we got state 2. Now, state 2 is after that combustion process, and we do, or not, I'm sorry, after that compression process, and we do have an isentropic efficiency given to us. So we'll need to figure out T2S as well as T2. So state 2S and state 2. And I know that state 2 is going to require me to use the equation for that isentropic efficiency, which is 0.92. And then I know that this is going to be the ratio of the two works, the work input. Ideally for a compressor, I don't have to put as much work into it, so that's going to be the smaller number on the top. This will be CP times T2S minus T1 over CP times T2 minus T1. Perfect. So I should be able to get T2 when I'm ready for it. And I think, let's make this kind of orangey. All right, so as far as numbers that I'm using, it's going to be this guy, right? But I am going to need to get T2S first. So I'm going to use an isentropic relationship. T2S over T1 equals P2 over P1. That pressure ratio is given to me to the K minus 1 over K. Make sure you're plugging those temperatures in Kelvin. But I get a T2S of 658.99. And so when I plug things in, I should get a value of 609. Let me verify. Hold on a minute. 699.7, I believe. 691.97. 691.97 Kelvin. Okay. So now state 3, which is not given to me. However, this is right after that regeneration process. So what I'm going to do is I'm going to use my little equation for my effectiveness. So as Q regen is CP times T3 minus T2 over Q regen max, which would be what the temperature of that working fluid would be if it heated all the way up to the same temperature as T5. So the same temperature is the highest possible temperature it could be. So then this would be T5 minus T2. So 3 minus 2, 5 minus 2. I'm going to put that down here and just kind of have that in my back pocket. T5 minus T2. CP. Actually, I'm sorry, it shouldn't have been T5 minus T2. That should be on the bottom. Okay, so T3 minus T2 over T5 minus T2. And of course, those CPs are going to go away. So once I get T5, I'll come back and I'll get T3. All right, and that will go into my governing equations there. All right, let's go on to state 4. State 4 was the highest possible temperature in that cycle. They gave that to us, although a little indirectly. And I've got T4 is equal to 2100 Kelvin. And then we get state 5. So state 5 is going to be, well, not only do I need state 5, but I need 5S. How come? Because remember, state 5 is after that expansion process in that turbine. Ideally, the turbine would be operating isentropically, but I have an isentropic efficiency of 95% associated with that. And so I need to calculate. I need to use my isentropic efficiency to relate the isentropic and the non-isentropic process. All right, so which one's which work is which? Ideally, this is a work producing process. So ideally, you get a lot of work out of it. Ideally is that one right there, right? The bigger number. So this becomes, and we've already derived this, but this is T4 minus T5 over CP times T4 minus T5S. All right. And so I should be able to get T5 when I'm ready. That's going to be it. And then, of course, I'm going to plug that back in when I'm ready for that one. I'm going to plug that in right there. but I do need T5s first. So T5s over T4. This is the isentropic process that I'm describing. K minus 1 over K. So let's see what they told us in the problem statement, because they didn't directly tell us P5 and P4, the ratio between them. However, what you'll see is that because I have an ideal cycle with the exception of those isentropic efficiencies, I have no pressure drops, meaning that P2, P3, P4 are equal to one another, and P1, 6, 5 are equal to one another. All right, so then this is going to be P5. All right, so you can see P5 over P4 is just going to be 1 over 20. So 1/20th. So I get a T5s. Let's see what I end up getting. I've got 892.27. And this is in Kelvin. And then I should be able to plug things in and get a T5, which is 952.66 Kelvin. And then that allows me to get T3, which is 913.55. Perfect, perfect, perfect. All right. Now, state 6, not really necessary, I don't think, although I do, well, if I want to use this equation for my thermal efficiency, it is. So, yeah, let's go ahead and get it. So you really have, you've got two options for this. You can use your regenerator effectiveness. Option 2, you can use your first law applied to the entire regenerator, right? Where you have the sum of the m dot h's coming in minus the sum of the m dot h's going out. So going in, if I look at my picture here, so I've got things going in at 2, m dot h2 plus m dot h5 equals m dot h3 plus m dot h6. So clearly the m dots are going to go away. I could put things in terms of Cp delta T, Cp T2. I can, it doesn't matter. I can put things in terms of minus if I want to. H2 minus H3 on the left-hand side, which is T2 minus T3. And then on the right-hand side, H6 minus H5, which is T6 minus T5. It doesn't really matter, right? But you can solve for T6. I end up getting a T6 value of 731.05. Right. So I got that guy right there. And now I'm ready to plug things in and calculate these things that I needed in the little happy boxes here. So I do have this guy is 62%. The Q dot N, oh, good question. But I have it. I don't know if I have the Q dot N, but I do presumably have a value for this other guy. I've got 44.2 megawatts. So, all right, and you should just be able to plug in and calculate that Q dot N. Just plug and chug. So if you would like to take a screenshot like that. All right, let's go to next problem. All right, so problem 8. We have air enters the turbine of a gas turbine at 1200 kilopascals and expands to 100 kilopascals in 2 stages. So it ultimately expands to 100 kilopascals, but we have 2 stages. Between those stages, the air is reheated at a constant pressure of 350 kilopascals to a final temperature of 1200 Kelvin. Expansion through the turbine, the expansion through each turbine stage is isentropic, and we want to determine in kilojoules per kilogram of air flowing the work developed if the air is expanded, yada, 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 as described in case A. And then we want to look at, well, what would happen if we just did it in one fell swoop? We went from 1200 Kelvin 1200 kilopascals to a final pressure of 100 kilopascals. What type of work output will we be looking at? So we're just going to compare the two and see if reheating works, because that is exactly what we're doing between those stages. Here is my QN for that guy. So we're not looking at a cycle here, but we're just trying to prove to ourselves that reheating does what it says that it's going to do. And I have went ahead, I wrote the first law up here just so we can reference it. For all of these, we're going to ignore we're going to say it's steady state, and then we're going to ignore kinetic and potential energy changes. All right, so I need to figure out for case A, same thing. What is that work output? And it's going to be for both of them, right? I've got two stages. So my work out, if I apply my first law, right? Oops. And I realize, whoopsies, that's not work out. It should be work in. I think I had the same typo on the previous one. I'm sorry about that, but work out minus work in. So the work out, it's going to be the stuff going in minus the stuff going out. If I put this in terms of little w, this is going to be, all right, going in minus going out. I'm going to have CP times T1 minus T2 plus CP times T3 minus T4. All right. And then for case B, I'm going to have work out. It's going to be a little bit easier, isn't it? It's just going to be CP times T1 minus T2. So I'm just going to look at these two cases separately, because I'm going to have a 1 and a 2, and the 2 is going to be different, yeah, on the left-hand side versus the right-hand side. But all right, so I got T1, I've got T3. I just need to figure out what T2 and T4 are. So state 2, and we said both of these guys, this isentropic efficiency is 1, same thing with this guy, same thing with this guy. We're not worrying about that. But the state 2 ends up being, well, got an isentropic efficiency of 1, so T2s and T1 are the same, so I use an isentropic relationship. So T2 over T1 is equal to P2 over P1 to the K minus 1 over K. I know what K is. K is 1.4. I know T1. I know the pressure ratio because I know each of those pressures, right? So I could just directly calculate it. And I've got a T2 of 843.9. 843.9 Kelvin. And it's the exact same process for state 3, right? So T4 over T3 is equal to P4 over P3 to the K minus 1 over K. And I know P4, right? P4 is 100 kilopascals. P3 is 350 kilopascals. T3, as long as I'm plugging it in absolute temperature units, that's great. And then T4 ends up being 589.99 Kelvin. And so I can calculate that. Let's see what I end up getting. It's a good question. Hold on. Okay, just kidding. Just realized I wrote something down wrong, or I typed something in incorrectly. So T4 838.99 is not the 500 number. And so when we plug things in, that work out becomes, let's see, 720.7. So 720.7, and the units there are kilojoules per kilogram. So that's going to be for case A. And then we look at case B, the work output for this guy. So, all right, well, T2 is going to be different now because we're looking at a different pressure ratio. So if I look at state 2, this is going to be, all right, T2 over T1. T1's 1200, and it's going to be P2 over P1 to the k minus 1 over k. But now my P2 over P1 is 100 over 1200. So my T2 ends up being 589.99. So I think that's where that number that I wrote down came from. And so if I plug things in, I end up getting a value of 613.1. And that's going to be kilojoules per kilogram. You can see there's about 100 kilojoules per kilogram difference. We get more work output when we divide up that expansion process into two and add a stage of reheat in between. All right, so let's go to the next and the last problem. All right, so I've changed the very last problem to be a little bit simpler as far as the isentropic efficiencies go. So let's kind of walk through it. Notice number one, I changed all of the isentropic efficiencies to 100% and the regenerator effectiveness of 100% to 100% as well. And that's because I kind of want to focus on this pressure ratio because that's the thing that's going to trip people up. But what you see is this cycle, which has got intercooling. Let's go ahead and draw that. So between the two compressors, we're fighting against what's happened, right? Pressure goes up, temperature goes up, but we're going to fight against that and reject heat. There is our Q out. And then between 4 and 5, there's a regeneration. So there's not a Q in or a Q out that leaves the cycle there. Between 5 and 6, that is our primary combustion process, which we are going to be modeling as a Q in. I realize that this should be a here that's a work in. Yep. In fact, speaking of the work ins and workouts, there's a work in here. There's a work in here. There is a workout right here. And there's a workout right here. So those workouts, work-ins, Q-ins, Q-outs, we got one more Q-in, actually two more Qs to deal with, but all of those, you're going to apply your first law and figure out, which comes first, right? It's going to be a delta H, which we will approximate as a CP delta T, since we're going to make cold air standard assumptions. And so it's, that first law is going to be what tells you which temperature or enthalpy comes first. Okay, so let's go to the heat exchanger between 7 and 8. This is our reheat combustor. This is the place where we're modeling that combustion process, that reheat process between those two turbine stages. So pressure goes down as you expand, pressure goes down, temperature goes down, but we're going to try to combat that and add heat. So there is our Q in. And then, of course, we have this loop, but it's not really a loop. They didn't draw the whole thing, but that's okay. They don't have to, right? They don't have to. Actually draw it up here because I know that's my exhaust process, and I'm going to model that exhaust process as just a simple heat rejection process. So I'm going to put that guy right there. So here is my Q out. In fact, I'll go ahead and put those governing equations for the Q ins and Q outs right now. So the Q out is going to be a CP delta T, right? It's delta H or CP delta T, and this becomes CP. This is by my first law, T10 minus T1. This Q out by my first law becomes CP T2 minus T3. Work in. This is a CP T2 minus T1. This work in right here, CP T4 minus T3. I have a Q in over here. It's going to be my CP T6 minus T5. Got some workouts over here, so it's going to be in minus out. CP times T6 minus T7. This guy is going to be CP times T8 minus T9. I thought I could fit it in there. I could almost get it. Almost get it. There we go. And then my Qn is between 7 and 8. It'd be Cp times T8 minus T7. Perfect. So I've got all my kind of general equations for the Qins and Qouts. Perfect. Now I need to figure out my governing equations. So thermal efficiency. You can calculate it in terms of work net out over Qn. I'll put that as green. So work net out. That would be this plus this minus this minus this. And that's a good exercise to go through. Make sure you get the same thing over the Qn. I'm going to define that Qn momentarily because I'm going to actually define my thermal efficiency in terms of the Q out over the Qn. So I've already defined all these things. My Qn, I've got two of those. There's going to be a Cp times T6 minus T5 minus, and it's going to be this guy right here, so T8 minus T7. And then on the top, I've got this source and this source. So I have Cp times T2 minus T3 minus plus T10 minus T1. And I'm sorry, I realized what I did. Somebody is confused. Like, what? This should be a plus because we're adding them up. That's a plus. Sorry about that. And so I'll just kind of put a happy little cloud right here. That right there for the thermal efficiency. Next thing I'm supposed to do, figure out my W dot net out. Okay. So I could calculate this. This is my, well, I've got an M dot, right? It's 6 kilograms per second. So M dot times little work net out. You could also, if you'd rather, you can calculate it as Q dot net in if you want, right? That would be any of the Q in minus any of the Q out. You should get the exact same number either way you do it. Since I've already defined Q in and Q out, I guess I'll keep with, no, I'll write it like work net out, but you should get the exact same thing again. So work net out, I'm going to have, so there's going to be a CP and some delta T's. So I have 6 minus 7 plus 8 minus 9 plus, actually not plus. So those are the work outs minus both of the work ins. T2 minus T1 minus T4 minus T3. Perfect. And so that should get me things, if I plug in everything just as I have, the mass flow rate in terms of kilograms per second, that Cp in terms of 1.005 kilojoules per kilogram K, I should be getting things in terms of kilowatts. So I'll put a spot right there for him. Very last thing I need to do, back work ratio. I guess that should have been the second thing, but that's fine. So it's going to be work of the compressors over the work of the turbines. We've already calculated this. It's just a, got a Cp times T2 minus T1 plus a Cp times T4 minus T3 over the Cp times T6 minus T7 plus the CPT8 minus T9. And we'll get a percentage here, and that will be fine. Perfect. All right. So the strategy of walking through the cycle is exactly the same it is before. I mean, we have a lot of extra terms because it's, there's lots of little steps, but at the heart of it is the same kind of thing going on every time, right? The same methodology. So from 1 to 2, we have an ideally isentropic process. Let's go ahead and handle that. So, right? So state 1, go ahead and write that. State 1, T1, 300. Is that what it was? Yeah, 300. Now I got state 2 or state 2s because state 2 and state 2s are the same since I changed it to have an isentropic efficiency of 100%. And so awesome, I'm just plugging along. T2 over T1 is equal to P2 over P1 to the K minus 1 over K. And here's where I run into an issue because if I look at my problem, if I look at this guy, uh-oh, I'm given some information here. I am told, and let's actually look at their problem statement here. So what it says, if I look at the problem statement, it says the overall compressor pressure ratio is 10. That's this one right here, overall compressor ratio. So from P1 to P4. All right. The pressure ratios, oops, that. The pressure ratios, darn it. Fine, there we go. The pressure ratios are the same across each compressor stage. So that's this little piece of information. So P2 over P1 and P4 over P3 are exactly the same. Then the next thing it tells me, it says the intercooler and the reheater both operate at the same pressure. All right, so that's this little piece of information right here. P2, P3, P7, P8. They're all operating at the same pressure. Okay. And then I've got one more thing that I'll highlight here. It says, there it is. Each turbine has the same pressure ratio as well. So what it's telling you is that the pressure ratio from 6 to 7 is the same as the pressure ratio from 8 to 9. There's a lot of wording in there. So make sure you kind of map that to what we've drawn on our diagram here, because that would be something that you would be responsible for doing. I would basically give you a blank a blank schematic like this, blank schematic like this, and I'd have some numbers on there, but I wouldn't draw anything else. It would be up to you to kind of fill in the information that's stated in the problem statement. So make sure you sort of read that and get comfortable with that. All right, so I don't know what the pressure ratio is from P2 to P1, but I do know some things. So I know P4 over P1 is equal to 10 because they told me that, right? That's something they told me. I also know, let's see, another thing I could do is I could say, let's put this, so I'm going to put the same number in those blank spots on the top and the bottom, and I'm going to pick P2. Okay. Right, haven't changed anything, nothing's happened. Now the other thing that I can say is that P2 and P3 are the same, right? So what I'm going to do is I'm going to rewrite this. This is now P4 over P3. Why? Because P2 and P3 are the same. I haven't changed anything. All right. And then the other little piece of information that I have is that that pressure ratio, P2 over P1, P4 over P3, they're both the same. Both the same. So this guy and this guy are exactly the same. And so I could just rewrite this as P2 over P1 squared, right? And so as a result, now I could just say, well, P2 over P1, that's the square root of 10. And that's the same as P4 over P3. And so now I can solve. So I get that T2 is equal to 416.8. 416.8 Kelvin. Perfect. So I need that one. I'm going to need that one. State 3, state 4. All right, so state 3 is given to us, and actually state 3 and state 1 are exactly the same. And what we'll see, since it's the same operating conditions and the same inlet conditions, when we plug in our numbers, it should not surprise us to see that T4 and T2 end up being the same. Okay. So this is all, now it's just sort of downhill because we've done all of this stuff before. Let's do state 5. So state 5 is right after that reheater. And for the other problems, when we had a problem with a reheater, well, that temperature right afterwards, we use the regenerator effectiveness equation. So, well, I know the regenerator effectiveness, right? It's Q over Q max, or Q regen over Q max, right? Which is, so this is CP times, looking at this guy, it's going to be T5 minus T4 over CP times the temperature that this guy would be if he were at the maximum temperature, if he'd heated up all the way as hot as he could get. And that's the same as this temperature right here, which is T9. So T9 minus T4. So what I'm going to do, I'm going to go back down here and just rewrite that. So my effectiveness, CP times T5 minus T4 over CP times T9 minus T4. I do need to get T9, but once I do, I'll be able to get T5. All right, moving right along. Almost there. So state 6. State 6 is given to us. So T6, 1400 Kelvin. And by the way, just so we're not too worried, we'll see that state 8 is also given to us. So T6 and T8 are the same. And it is the same operating conditions and the same inlet conditions. So we'll find that T7 and T9 are the same, but let's prove that to ourselves. All right, so let's go back. I know from 6 to 7, I've got an ideally isentropic process, so I can use an isentropic relationship. So this is going to be T7 over T6 is equal to P7 over P6 to the K minus 1 over K. What's P7 over P6? Well, let's see. So I can do kind of a similar thing here. So I know, kind of look at the pressure. So I know this guy, right? I know P4 over P1 is equal to 10. Well, I also know P4, P5, P6. All of those are the same. So P4 and P6 are the same. And then looking at P1, P1, P10, P9, all of those are the same. So I kind of have a similar um, pressure ratio, kind of an overall pressure ratio here. So let's do the same thing. And I also know you can do that. It's a very similar kind of strategy that we took for calculating P2 over P1. So I don't know P7 over P6, but I know I wrote it as P6, P6 over P9. Let's write it as P9 over P6. So P9 over P6. I know that's equal to 1 over 10. Right? Going to do the same thing. Okay. So this time I'm going to rewrite it. This is going to be, hopefully you have your picture in front of you, but let's see. So P, let's put this as P7. Okay. And then I know between 7 and 8, that is the same pressure. So I'm going to rewrite this as not P9 over P7, but P9 over P8. And those two pressures were told to us to be equal to one another. Those are the pressure ratios across each of those turbines. And so I could rewrite this as P7 over P6 squared. So now I know P7 over over P6 is just equal to the square root of 1 over 10. And so now I can get T7. So T7 ends up being 1007.56 Kelvin. So that's one of the things I need. And remember, this is the same as P9 over 8, right? Same thing. And so same isentropic relationship, right? T9 over T8 equals P9 over P8 to the K minus 1 over K. And I'll get that T9 and T7 should be exactly the same thing. So when I plug things in, I know we're a little bit over, about 15 minutes over, but that's all right. Better late than never, right? I got a thermal efficiency of 70%, 70.2%. I've got a W dot out 3.6 kilowatts and a backwork ratio of 29.8%. All right, so if you would like to get a screenshot of this, I'm going to try to get it so that the highlighted stuff is there. There's one screenshot, and there is the other. All right, hope that was helpful. Let me know if you have questions. And yeah, I will have office hours Monday morning, class time, no class, right? It's just a day to study or to take your test if you'd like. But again, I'm delaying that test due date until Tuesday night, just since we didn't have as much time this week since the semester started on Wednesday. So, all right, good luck studying. Let me know if you have any questions. Thank you.